All right. Hello, everyone. So welcome to part 2 of the Logic video lectures series. So in this one, we're going to be expanding a little bit on some of the things I addressed in the previous video lecture and kind of going a little bit more into depth into the logic behind research essays. So the first thing to kind of think about, and something that can come in handy when you're creating a thesis statement, is to think about a conditional statement. So that's a if-then statement. So if X, then Y. So if this thing happens, then that thing happens. And we'll go into some of the other flaws in here, in particular causation and correlation. So if you're kind of thinking that already, great. If you're not familiar with that term, then don't worry about it. I'm going to unpack that a little bit more. So another way to think about this is if X, so if there's something and I see something else, then Y must be true. So what does that kind of mean? So let's take a look at a very serious example. So if I take the penguin's ice cream cone, then it will be sad, right? So that's a conditional statement. That's an if-then. Now, my observation is I took the penguin's ice cream cone and the penguin is crying. Then my conclusion is it is crying because I took its ice cream cone. So there seems to be a direct causation here, something that has caused something else. There are other varieties of this. So another example, if things that are combustible catch fire and paper is combustible, then the paper will catch fire if I hold a match to it. Or another example, if it is raining outside, we will not go outside to play. It is raining outside, so my observation, therefore we will not go outside to play today. Now, it's worth noting that the opposite is not necessarily true. So what we need to be aware of is we can't just flip these things around and expect it to still make sense. So if I look at the opposite of that original statement, we would say we are not going outside to play today. When it rains, we don't play outside. Therefore, it is raining. Now, that might be true in some circumstances, but it could be the zombie apocalypse, right? There might be other reasons that we decide not to go outside and play. So again, we want to make sure that the order is correct, because this reversed statement, the we are not going outside to play today, is the opposite of the reverse, which is what we looked at in the previous slide. Now, if we kind of think about this and the error that happens, so this is where I want to dive a little bit more into how logical reasoning works, is we could do a couple quick tests. So let's look at the first one. Old men are often bald. I think most of us could probably agree with that statement. It's not always true, but it does seem to be true sometimes. Then we could say, well, Joe is bald. Now, if we're following this train of logic, then that would mean we would conclude that Joe is an old man. Well, that might not be true. Again, there could be any other number of reasons why Joe is bald, right? Alopecia, or maybe he bicked his head, clean shaven, whatever it is. A similar one would be, and hopefully you're beginning to think of like logical fallacies here, some of the mistakes that people are making. My math class last quarter was awesome. There are a lot of different math classes on campus. Therefore, all math classes must be awesome. Now, this is what we begin to see as a logical fallacy, and one we're going to talk about a little bit more. And in this case, it is called hasty generalization, or you could think of it as kind of a stereotype. So we're going to skip over the next couple slides here, which I usually do in an in-class setting where we unpack kind of two different arguments, but I'm going to skip over it here just for the sake of interest. Okay. Oh, one more. Come on. All right. So what we can get to, since we've been talking about if-then statements, is, again, how we formulate an argument. And this comes down to, again, how we begin to present information. And there are kind of two methods that we frequently use, and they may be familiar terms to you: inductive reasoning and deductive reasoning. And there is a reason that I want to go over these. It's primarily food for thought. as you begin to construct your research and as you begin to bring all the research together and construct a logical argument. And I don't like using the word argument, but is the best one that we can use in this particular situation. So let's kind of start by defining reason. All right, what is it when we say we are reasoning? Not just, because reasons, but what is reason? So let's just take the Merriam-Webster definition. Definition number one: to use the faculty of reason so as to arrive at conclusions, or to talk with another so as to influence actions or opinions. If we think about logical reasoning that we're doing in a research paper, it's really both of these things. We're using our individual faculty, our ability to reason clearly and logically in order to arrive at a conclusion. And in doing so, we are also talking, quote unquote, because we're writing for other people, so as to influence actions or opinions, right? To know, do, or believe, right? What do we want our audience to know, do, or believe? So one way to do this type of reasoning is with what we call deductive reasoning. So that's starting with the assertion of a general rule and then proceeding from there to a guaranteed specific conclusion. Now, this one is a little bit trickier, and it only really happens in certain circumstances. So one we might think about, and my apologies for math-phobic folks out there, but deductive reasoning might be seen in math where we're moving towards certainty, right? So we're moving from a general rule to a very specific conclusion, and it's all based on the idea that the assertions that we have, the first couple claims, are true, and if we have true assertions or true facts, we're going to come to a true conclusion. So an example would be, let's say x is equal to 8 and y is equal to 2, then 2x plus 3y is equal to 22. So that would be deductive reasoning. We have specific facts and we're moving towards certainty, the certainty that that equation is equal to 22. So this kind of goes back to Aristotle, where we have true premises and we come to a true conclusion. And of course, the premises have to be true in order for the conclusion to be true. So if we say that all men are mortal or all humans are mortal and Socrates is a human, then we can conclude that Socrates is mortal. Now you can think back to the Joe being bald example and old men being bald. Very similar concept, right? We have these conclusions or these premises that are leading us to a conclusion. Now, a flaw in that premise, that little fact, can lead to a flaw in the conclusion. And there are kind of steps along the way that can go astray. And that's where we get to logical fallacies. But I want to make sure that we have a nice solid foundation before we move on to those specific logical fallacies I want to talk about. So deductive reasoning, if that's still a little bit hazy to you, you can think of it as this inverted triangle here, or inverted pyramid, where I could create an argument that looks sound, but is not, right? So if I said, in general, someone must win the lotto, and I am someone, I could come to the conclusion that I will win the lotto. Now, odds may not be in my favor, right? So again, when we have this, we're going from a generalization to something really, really specific. And we need that chain of events, like that information, to be very logically presented, and it all has to connect. Now, what we use more often in research writing is what we call inductive writing, or inductive reasoning, sorry. So inductive reasoning begins with observations that are specific and maybe limited in scope and proceeds to a generalized conclusion that is likely but not certain in light of accumulated evidence. Now, why might this be? Well, we can't get all of the information, right? We are only going to be able to get what we can in the limited amount of time that we need to research. So in inductive reasoning, our goal is to discover the most likely conclusion, right? The most likely cause of increased anxiety in teenagers is social media use, or something like that. I can't say it with an absolute certainty unless I've done a lot of tests, and it's probably going to be beyond the scope of what we're going to do here. What we are going to do is we're going to begin with specific observations that may be limited in scope because we're sort of assuming or presupposing that things aren't changing, that they're remaining somewhat the same. And we really have no way of knowing if we've gathered all of the evidence that is available to us. In fact, we probably won't be able to. So again, one more example. If disorder in a system increases unless we do something, unless we expend energy, and my living room is a system, then I can assume that disorder is going to increase unless I clean it, right? Now, is there maybe other evidence that I haven't taken into account? Yes. Are there other possibilities? Yes. But for all intents and purposes, we've got inductive reasoning at play here. So just a couple things and then we'll wrap up this video. So inductive reasoning, again, if you just need a visual, if you're a visual type of person like I am, this is the opposite of deductive. So we're moving in the opposite direction. So the example I would use here is, again, something more like math, but it's kind of more statistics math, right? So let's say I have a bag of coins and it is an opaque bag. I cannot see through it. And I reach in and I pull out a coin, and that first coin is a penny. Then I reach in a second time and pull out a second coin, and that is a penny. I could come to the general conclusion that all coins in the bag are pennies. Now, of course, there are a number of things at play here. The easiest way to find out if all of the coins in that bag are pennies would be to simply dump it out and look and see what I have. But again, in the analogy, that would mean I would have all of the evidence, which is very, very rarely true and very difficult to do. So what I'm doing is I'm going from generalizations. Now, what changes is how many coins are in there. If somebody said, hey, Michael, here is a bag of 100 coins, and I wanted to be as certain as I could be. My goal would be I want to get as many coins out of that bag as I possibly can to increase the certainty. Because if I take one coin out and it's a penny and there are 100 coins, I only have a 1% of the big picture, right? And the more I pull out, the bigger percentage that I have of that overall topic. Hopefully that makes a little bit of sense. Again, these methods are not insurance that we're going to get everything right. But if we kind of understand that what we are generally doing here is inductive reasoning, then we're moving towards certainty. And a really fantastic quote on this that I'm going to leave you with is from the quantum physicist Richard Feynman, really brilliant individual. And he said of the scientific process, we can never be right. We can only be sure we're wrong, right? So, as we're testing something, we can be certain when we have evidence that says, okay, we are wrong, but we never know that we're absolutely right because we don't have all of the evidence, and some evidence that we get tomorrow or next week or next year or in the next 10 years might change our thoughts. So all we can do is get as much evidence as we can to make sure that we are not wrong. And if we are not wrong, we are maybe closer to being right. So there you go. If you have questions, comments, concerns, jokes, memes, or recipes, please let me know. Otherwise, I'll talk to you all in the future.